So where are we, right? We have this function that's described in terms of this neural net. We have an actual task, which in our case is a regression task, where we have n samples, capital L samples, and we are looking to minimize the L2 norm. Now, we could add very simply to it an actual, an actual term for regularizer. This wouldn't really change anything, so I'll just keep it out, but it would be trivial to change if you had this extra regularization term. And now, remember, we have these many parameters, right? They're essentially something like k squared times L parameters that we have in here. K is being how many nodes we have per layer. It's a fully connected network, so it's k squared per one layer, and we're having L layer, so it's roughly k squared times L. And when I write down that we want these partial derivatives, I don't mean that we need two partial derivatives. We need these k squared L partial derivatives, right? For all small l going from 1 to capital L, and for all I and j going from 1 to k, right? So we need a lot of derivatives. So this could be 1,000,000 derivatives that we need. Clear? Scope of the problem is clear? Okay? So, and now we want to do this in a smart way. And so let me first just write down this function in a slightly more compact way. So if I'm thinking of this overall function, right, f of x0, and I'm going to omit now the n for the sample because just too much writing. But I just have some input, and for this input, and this is the input on the very left, x0, then this is the following, right? So I can write this down as f, let's say, 1 of x0. So this f1 is whatever function is implemented by the first layer. Okay, and we're going to write this down in a more compact way. So this goes from x0, the first layer, which is just these connections, the sums, and then add the bias, and then apply this activation function. So the result of this is what we'll call x1. Okay, so that's the output after the first layer. That's what's in this first layer. Right? Now this gets composed. The next thing is that now apply the f of 2. Right? So now this input, whatever comes out of here, is now input into the second layer. And now I do again summing, adding bias, applying the nonlinearity. Right? And what I get out of this thing here will be the x2. Right? And so this goes until I have the f of L plus 1. Is this clear? Right? So this is just a composition of many relatively simple functions. And so what does one such simple function look like? Right? So let's assume I have f of L. Okay, so f of L takes as input x of L minus 1. Right? And the output will be the x of L. Right? And we have already written down what this thing will be, but let's be explicit. XL is equal to, let me just write it down and then we'll talk about it. Okay, so this is WL, it's a matrix transposed times x of L minus 1 plus B of L, and then the phi applied to it. Okay, so this is in vector form. In vector form, I claim that going from 1 to the second input, I can proceed like this. This is a whole vector here of length k. This is the vector here of length k beforehand, right? This represents summing up, the summing of this network here. This is a vector of the biases. And then this is the function that component-wise applies the activation function, right? So what is this W here that I have? Well, this WL is a matrix here. It's a k by k matrix. And its ith, jth entry is exactly what we had called, I can't even make a distinction on the board, is exactly what we had called the weight Lij. So let's just draw this again. So let's assume this is here the x, L, the jth one. And so this is the previous layer. This is x of L minus 1. Then what are the weights here? If I'm looking here, I have W of L of I and j. These are the weights, right? And what was this? This we said was just the activation function applied to take all the sum of the inputs, the weighted ones. So I go from I is 1 to k. I look at the x of the previous one, the I multiply it by the weight that goes from I to j. At this, I add the bias term and apply the activation function. Right? So this is what we had written. Right? So again, in order to get this, take all the inputs, take every input, multiply it by its weight, sum all these things up, add the bias term that we have, you get the whole sum, okay? And now apply the nonlinear activation function. That's it. Okay, and so the only thing that we did now in writing this in vector form is that I write this sum here, right? The sum that I have here, I write it now as a matrix times a vector, right? That's the only thing that we have done many times. Everyone with me? So this means that we have a bunch of very simple functions. Right? So, and as we go along, we start with x0, the vector. We compute the x1, right? We compute the x2, and we simply go until we at the end the output. Okay? And now the task will be the following. At the end, what we're looking at is at the output, right? And more specifically, what do we look at the output? We're looking at the output f that we get of xn. So this will be the small x L plus 1. And I'm looking at how different that is from the y that I see. Take the square. And now what does it mean to take the derivative with some parameter? Well, it means that if I tweak this parameter a little bit and did the computation again, I would get a slightly different output. And I want to see by how much this changes, right? That's what we're calling the computing the derivative is, right? Very simple. So now, so in order to do this, we do this in two passes. Okay, rather than trying to write down directly what the derivative with respect to the parameters that we're interested in, that would be quite a mess. There's a much nicer way to doing that. We see automatically a recursive structure, right? So the first thing that we want to do is we want to take this one here and we want to split it into just two parts, okay? So we can see here, so what we want to do is the following. We're going to compute some other parameters, which are called ZL. So these are again vectors. And what is CL? CL is essentially like the XL, but it's before we have taken the nonlinearity. Okay? So this means the ZL is just this result of this linear thing. Right? But I have not taken yet the nonlinearity. So I have the ZL and I have the XL. And the XL is simply the nonlinearity applied to the ZL. Clear? So it's just convenient to write down. We'll just see that it's nicer to take the derivatives first with respect to the ZLs rather than XLs. It's just nicer that way. Okay, so now the forward pass is very simple. Okay, the forward pass is very easy to do, and we see what the computational complexity is. I start with the x0. The x, remember, this corresponds to one sample. Okay, it's some vector, right? I start with this. From this, I now compute the z1, right? How do I compute the z1? I just multiply this vector by the matrix, which corresponds to this first network that I have, right? The first transition from 0 to 1. Then I add all the bias terms to it, right? I get a new output vector. That's a length k vector, right? So I'm moving from the left to the right. Then from this, right, so we've seen how to do this. Maybe let me write it down once more explicitly. Okay, next I compute the x1, which is just the nonlinearity applied component-wise to the z1. Right? That's trivial. Just apply component-wise. And now I go on, right? So now I have the output here. So now it's just a recursion, right? I compute the z2, I compute the x2 from it, and I don't write down what this is. It's obvious. Until at the end, I get my zl plus 1, and I get my x l plus 1 being some phi of zl plus 1. Okay? So that wasn't too painful, right? And we're already done with half the algorithm. Okay, now we have to just do a backward pass. Slightly more complicated, but not much more. So what is the computational complexity? Well, we have to multiply at every step. The dominant term is that we have to multiply with this matrix here, right? And so we have to take this vector and do the matrix multiplication here, right? And so that's the dominant thing, and then we have to do this L times, right? So it means that complexity is something of order k squared, because we have k squared entries here, and then we have to do this L times, and then all the rest is kind of easy because that's just for each component, right? We have to do this, okay? So complexity is something of order k squared L operations, right? So that's not too bad. It basically means we have to touch every edge once, so do one computation per edge. Good. So now let's go to the backwards thing here. Okay, so now, yes?
Matrix multiplication is k-squared.
Sorry?
The matrix multiplication complexity is k-squared.
So, well, I take each of these fk, right, and I multiply it with the top row, right? So I have k entries I have to multiply and add, right? And then I do this for each, and I have k of these rows itself, right?
But it was k-cubed for some reason.
If you have matrix by matrix, right? But we have a vector by matrix. Okay, good. Okay, so now, now we do the backward pass. So for the backward pass, we want to introduce one extra quantity. And so this quantity is a delta, again, L and J. So there's one for each node in this thing. And what is this? This will be the following quantity, the partial derivative of our cost function that we have with respect to these things that we just introduced. Okay, so remember, the z was just the input, was just the input at the elf layer just before I take the phi function, right? So it's essentially the x at this layer, but before taking the phi function. And now what I'm computing, and it turns out that that's kind of nicer to write down, I'm computing the derivative of the output, assuming that just this input to the phi function at the jth node at the elf layer changes. And I call that delta L j. Okay, so these are quantities that I would like to introduce. Okay, and so it turns out that in terms of these two quantities, we can now proceed. Okay, so let's check. So now what we want to do is we'll do a pass. We basically assume we start at the back, and we'll see what the initialization will be. But what our aim will first be to computing these things recursively, And once we have these things computed recursively, we see that in terms of these entities, it's very easy to compute what we're actually interested in. Okay, so the whole key will be to find efficiently these quantities, and then once we find these quantities, we'll see that it's very easy to compute the quantities that we're interested in. Okay, so we want to compute things now backwards. So let's say dj L. I want to compute this. So this is the dl dcj of L. And so now I'm going to write it down as follows. I'm going to write this down as the following. K is 1, or I guess we had I here. I is 1 to k. And I write it down as dl of zj of L, or C, sorry, I of L plus 1 times dci of L plus 1 over dcj of L. Okay, so what do I do? So remember what I have. So I have here my layer L plus 1. I have here my layer L, right? I have somewhere here the end here, and this is related to the cost function. And now remember what these quantities are, okay? These quantities are the following. It's the derivative of the final cost function, right? So if I'm looking at this term here, this layer, sorry, I want to compute this thing here. Maybe it's this thing here, so let's assume that's J. And I have here the input. So what is it that I want to compute? What is this quantity here? So remember, the computation comes back here, okay, goes on. And now what I'm saying is the following. If I slightly changed how much input I would have here at this point, so I had a knob, and I could slightly change how much input there is, how much will this change the output that I have here, right? So that's a forward computation I do. I have some values here, I compute them, and then I take the same values here, but slightly tweak this input here by a little epsilon. Again, do the forward computation and see how much difference this makes. Okay? And so what this formula says is the following. Rather than doing this, I do the following. For each of these quantities, I'm checking that if I change slightly the input to this node, how much would the output change? I change slightly the input to this node, how much would the output change? And now what I'm saying is the sensitivity of the output compared to this is the following. If I change the input here slightly, right, then this, since this is connected to all these inputs here, will change each of these inputs here a little bit, right? Right? And now each of these inputs, I know already by recursion, will change the output like this, right? And since everything is infinitesimal, the total change will just be the sum of all these changes. Clear? So this is the change that I see here, which presumably recursively I've already computed, right? And this is how much, if that input changes, how much will the input to here change, right? So now if I have this thing here, we already know what it is, right? Because by assumption, we already recursively computed it. This presumably is the delta L plus 1 I, right? So I presume that recursively I already computed it, right? I start somewhere here. I will have some initial condition. I already know what it is here, and then I recursively compute it backwards, right? So this I can assume that I already know it. So now the only thing is, can I figure out what this thing here is, right? So by how much does this, how much does this change? So let's just check here again, right? So if I'm taking here a particular node here, let's say this is node I. Okay, so I have here Z L plus 1 I, right? So by how much does the input to this node change if I change a little bit the output here? By how much does the input to this node changes? Right, so I'm looking here now at d z I L plus 1 over d Cj of L. So forget about this. Let's assume at the output here I changed the value slightly by an epsilon. By how much was the input here change? Well, is anything happening from here to here? What is the function associated to this edge here, from here to here? It's the weight, right? So I have the weight here associated, right? And this weight is WL plus 1, and it goes from J to I, right? That's the weight, right? So this means there will be a factor WJ, right, of L plus 1 and I that I'll have here, right? Good, but that's not all that's happening, right? So, when I change the input here a little bit, I still take the phi function here, right? So how much does the output change if I change the input a little bit? Right? So what is the input here? I have x of L here, right? I have x of L, and then I'm looking at the jth term here, right? And and the output here will be, sorry, I have the z, okay? And now I take the phi function of it, right? And now I'm saying I'm changing this value here a little bit. By how much will the output change? Well, if a function at a particular point, I'm taking the derivative, right? So it means I get this times the phi prime of, and where? Phi prime of this z of L and J, right? Is that clear? Fine? Okay, so now I just need to put this all together, right? So this means I have this, and then these two terms are just this Wj, this thing here is this Wji at L plus 1 times phi prime of Zj. Okay, and so we see that we have an explicit expression, and this expression is not complicated. It's an explicit expression for this derivative here. Once I know all the derivative associated to here, just by going backwards now, I can compute all the derivatives here. And what is the computational complexity? Well, for each of them, right, I have to go to all of those. So again, I have to touch every node, every edge once. So it's again a complexity of order k squared per section, and then I have L such sections. Okay, so let me just write this down now in matrix form. It looks a little bit nicer. So if I write this down as a whole vector, I get this, and I can write this down. So this is again my matrix here, L plus 1, delta, L plus 1. So it's just a matrix multiplication. Okay, so what does this mean here? So you see here, this and this is exactly what I have here, the multiplication of this with this, right? Now, what does this mean? This just means pointwise product. So this itself is a matrix times a vector. I'm going to get a vector out. And then I multiply this vector pointwise with this vector. Okay, it's just a compact way of writing it. There's nothing, this is no different than this. I haven't done any math, I've just done notation. Fine? Good. Okay, so now we are basically done. Now we just need to see how, with respect to, I guess, So we have two passes now, right? We have seen the forward path. In the forward path, we're computing, I guess I deleted. In the forward path, we're computing x0, z1, x1, z2, x2, and so on. In the backward path, we're computing, starting from the very back, and we still have to talk about the initialization, the derivatives, right? So we're computing these partial derivatives here, right, of the cost function with respect to the z variables. And we do this now backwards, okay? So we started here, and then once we have the derivative here at this level, we compute the derivative here, right? Then we compute the derivative here. We go back until we're all done. So now the only thing we still have to do is we're not interested in these derivatives per se, right? We're not interested in the derivative of the cost function with respect to the variable z. We're interested of the derivative of the cost function with respect to the various w's and the various b's, right? And so we still have to see how to write this down. So what we really want is, let's say, the derivative of the cost function with respect to the d, w, let's say, l, I, j. And so we're gonna, now what we have to do is we want to again write it down, we express it in terms of these z's here. So we write it down here as again as a sum. I is 1 to k. And so I want the derivative, and the z's I want are the one on the same level. So I have z, l, and I have here I, and then times d of c I of l with respect to d, w, I, and j, and have here l. Okay? So again, it's the same trick. So let's see, let's just write down this figure here, and we see what it is. So so let's say that's layer L, right? And I see here, let's say, the zi at layer L. And then have here the w, maybe this is here the I. And I have here the w associated with this. I have w, L from I. Sorry, this is not I. This should be, just a second. I want the j second. Which one do I want? Okay, yeah, that's fine. So I want the j here. So I want here from I, yeah, so that's correct. So I don't want, sorry, so this is a very bad choice to do another I. That's what confused. I need here a k, and I want here a k, and I want here a k. Okay, so that's now fine. And now we go over all k here, and we're having here the ck, and we're having here an I, and then we're having here the ij. Okay, looks better. Good, so let's see. This thing here, right, we already know what it is, right? This is just by our definition, this is just the delta, right, of level L, and we're having here the k, right? So this is the definition, the derivative of the cost function with respect to the input here. So if we can figure out what this thing here is, then we can compute the actual derivative that we're interested in, right? Okay, so let's check, right? So what do we have here? So we have here the wij. So the wij means that it goes from level L minus 1 to level L, and it goes from node I to actually node j. Okay, so there will be also somewhere here the node j, and then node j here. Okay, and there will be weights here everywhere. Okay? And so associated to this edge here, from I to j, we have a weight here, right? wij. So the question is now the following. If I fix everything here, right, and now I tweak a little bit what the weight here is, okay? So I'm checking with respect to, what do I do here? I'm looking at how much does any of these inputs here change if I'm tweaking a little bit the value of the weight here. Is this clear? This is fixed, okay? I have some fixed values here. In principle, to compute the values from here to here, I just multiply by this matrix, add the bias term, and apply the phi, right? But now what I do is I do this once, and the second time I do it, I'll slightly tweak the value of the edge from I to j, right? So what does this change? Which of these values here will be changed? Again, fixed values here. I need to do the computation and compute what's here. Okay? Now, I take the same values here, but now I do it with this edge value slightly tweaked. What changes on the right-hand side? Just loud, please. Right? So the only thing that will change will be the input to this thing here, right? Everything else will be the same, right? And so the only value that will change will be this, right? And so by how much will that input here change? If I change the output, if I change this value here by delta, how much will this change? So beforehand, I had, let's say, a W, I, J, and L, right? And now I have a W, I, J, and L, plus, let's say, a little bit a delta, right? And so how much contribution here did I get from over this edge beforehand? What was the output here? Right? The output here was the x, right? Was the x at level L minus 1, and it was the I, right? I multiplied this by the W, I, J, L, right? And then I added, then I summed, and then I summed this up to get for the output here over all the possible I values here, but I'm just interested in this contribution. The rest stays the same. And then I added still the term, the bias term, right? Now I do the same, but now I add here an extra delta, right? So by how much does it change with respect to delta? I take this without the delta, right? Minus this with the delta. What's the difference? Right? It will just be, the difference will be exactly this thing here. Okay? So this means this derivative here should just be the x, and I have here, right here, yeah, so this should be L minus 1. This is correct. So this thing here is exactly x L minus 1, and it comes from J. Okay? Is this clear? So this will be, if k is equal to j, I get this, and if k is something else, I get 0. Okay, so I get this if k is equal to j, and I get 0 if k is unequal to j. Okay, so if we write this down, what do I get? Okay, so I get that my derivative, dl, with respect to dw ij of the L is just equal to this delta L of, let's have delta L of j, and then I have the x I of L minus 1. Okay, so once this means the following. The forward path gives me the x's. The backward path gives me the deltas. Once I have both, I just do one extra, multiply the two together, and I get the derivatives that I'm interested in, okay? So that's quite simple. And so we can do the same thing now with respect to this, right? So we can do respect to the B, whatever, B, I, and L. And if we do the same computation, what we get is that these just turn out to be the delta of I and L. Okay, so let's catch a breath, okay? So, yes?
Can you explain why you drove the sum term?
Right, because, so you're talking about here? Yeah. Yes. So, what is this? Okay, so up till here with the sum, you okay?
Yeah.
Okay. You also okay that we can replace this with this?
Yeah.
That's just a definition, okay? So now the question is, so what I'm saying here is that for all the terms except one, that's 0, okay? Why is that the case? What is this term here, okay? The term is the following. What you're doing is the following. All you're doing is you're changing for one edge the weight slightly. That's all you're doing, okay? And you're asking how much does this influence the input to the various nodes that I have here, okay? So you're asking how much does, if I change this weight here, how much does it change the input here, the input here, the input here, and here? But this edge goes from here to here, okay? So if I change the weight of this edge, and the input here is the same, then the output at all the other nodes will not change at all, right? So the only change will occur at that node to which this edge goes, right? And by how much will it change? Well, if I change it by a weight delta, I originally had here weight some x coming in. This x was multiplied by this weight here and came out here x times the weight. Now I change the weight from weight to weight plus delta. So this gets multiplied by the x, so the change will be x. Okay, and so that's exactly what I have here. Make sense? Good. So in the notes you find a nice summary. Okay, so let's go over again. We have this nice structure of a layered network. What we're interested in is to compute the gradient, so meaning the derivative of the cost function with respect to each of the parameters. The parameters are the weights, so it means the weights that I have on each of these edges, and the parameters are the bias terms that I have here. Rather than computing directly the derivative with this, what we're doing is we're first computing derivatives with respect to some other quantities which are nicely structured so that I can do a recursion. So what are these parameters? Remember, I have the x values. They have the x coming in. After one step, I get the x1. After 2 steps, I get the x2, etc. Okay? Now, I introduce a new variable, and the new variable is called z, which is essentially the x, but just before I apply the phi function. Okay? It's just the input to a node. So recursively, starting from the left, I can compute the input, then the z value, then the x value, then the z value, then the x value, then the z value, the x value, etc. Okay? That's the forward pass. Now, we go backwards pass. Okay? Now we introduced another parameter. The parameter was, how much does this cost function, how much does this at the end change if I'm changing a z value, one of these z values that I have, slightly? Okay? And so this derivative was called the delta. And the computation that we did up here shows us that I can now go from the end backwards. And if already at some level I have computed all these deltas, then I can compute the deltas at the previous level by this simple recursion. And that's what I wrote down here. Delta L is W, this times this, what's called the Hadamard product, the pointwise product. Okay? And we've seen that that's a simple recursion here. So I go backwards and compute all the derivatives. And of course, I memorize all the x values, all the z values, and all the derivative values that I have, right? And now the final task, so that's kind of a third pass that if you want to have to do, is now I have to convert that into my actual derivatives that I'm interested in. And so we saw in the final step that the actual derivatives that I was interested in, for example, the derivative of this with respect to one of the weight, can be expressed in a simple manner with respect to the derivatives that I already know, plus some extra value here. Okay, and we have seen in particular that if I'm interested in the derivative with respect to the particular weight on a particular edge in the alpha layer going from I to j, then this is essentially this derivative that I already know multiplied by the input that I also already know, right? And if I want to do the same thing with respect to some weight, again, that's essentially just a delta. So, we didn't call it like this, but this is exactly equal to the derivative of these deltas, okay, or derivatives of the c's. So the whole cost now is what? One forward pass, something like k squared L, one backward pass, something like k squared L, and then just doing the computation, which is even less because I just do one per node. So it's something like k times L. So the overall complexity is something like k squared L, which is proportional to all the edges they have in the graph. Okay? And so the gain that you do is that if you had done the derivative with respect to a single value, and you had done each derivative individually, then essentially you would have to have done the same computation we do now, but for every single derivative, okay? Because if you want the derivative somewhere of a node early on in the network, you basically have to do the same computation that we now, but we kind of structure the computation that we've done all the derivatives at the same time in a much more computational efficient manner. Okay, so if you hadn't done this trick, computational complexity would be like the square or something, or not like the square, would be a factor k times L larger, and that could make a significant difference because sometimes the number of nodes might be like 1 million or something there, okay? So it could be quite large. Okay. Fine, any questions? Good, okay, so next time what we'll do, we'll look still at various variations. We'll look at different tricks, like things like convolutional nets. We're looking at things like dropout and other tricks that people do for neural nets.